the issue with the latent structure model is how to estimate those parameters. And coding for is trying to ask you to code how to estimate a mixture of a Gaussian distribution is in two-dimensional space. So in that, in the mixture in coding for, here's our, let me do it this way. So we have our data, our density function. This is actually very much like our coding one. Our density function, x is two-dimensional, is actually a mixture of two normal. Can you see the thing I write down the paper clearly from your side?
Yes.
Okay.
Yes.
So this is probably P1 times a normal, meaning if you are in the first component, you're going to follow a normal distribution with mean mu1 and covariance matrix sigma. And a probability P2, you're going to from the second component. You're going to, from a normal with mean mu2 and covariance matrix sigma. Now here, what are the parameters? So this actually, I put a subscript theta. Theta
So
means
Professor, one thing, what does component means here? Like when we say P1 and P2?
Oh, that's a probability.
Yeah, it's a probability, but for, like you mentioned that these are for two components. So what does that component means? Like it's the eruption and the weighting, like that, or it's...
Yeah, you can think about the P1, P2 are weights for the two components. It's almost the same as in our coding one. We assume the data are generated from 10 components, and meaning every data points will be generated from one and only one of them. And in coding one, that weight is actually 1/10, meaning equally.
Okay.
So this could be 0.2, 0.8. If I tell you how, if I told you the parameters, how you generate data from this distribution, well, you're first going to actually generate a Bernoulli, like you toss a coin with probability of P1, you're going to say a head. With probability P2, actually P2 is always equal to 1 minus P1 because there are only two components.
Okay.
With probability P2, you're going to say a tail. Now, if you say a head, you generate data from this distribution. If you say a tail, the data will be generated from this distribution. Yeah. So the parameter is going to be P1, P2, mu1, mu2, and sigma. Here, P1, P2 actually can be merged as only one parameter because P2 is always equal to 1 minus P1. Okay. And now, in coding one, we're talking about how to generate data from this mixture distribution with the parameters are given. But now we are talking about if you are given the data generated from this distribution, can you estimate those parameters accurately, like the weights and mu1, mu2, and sigma. So we're sort of and play the game from another side now. So those are all the parameters you're going to you need to optimize. So in order to run the EM algorithm, let me first talk about, well, here's we have our data. It's going to be x1, x2, xn. They are two-dimensional in our coding assignment 1 as 4. And they are lowercase x. And each one of them, there is a latent variable, z1, z2, until zn. They are uppercase, although I cannot really, you can guess because they are bigger. And because they're going to be taking values from either 1 or 2. They're the latent states. Because once you show me the data, I'm not the one generating the data, so I don't know whether x1 is generated from this component or this component. Either one is possible. And so which component, the indicator for x1 is going to be latent because you don't observe. Okay. Now, let's first and look at how you compute this. So in the EM algorithm, you have to work with the joint likelihood, meaning x1 and z1. And what is another joint? The marginal distribution for x1 will be the sum of this. And we know, and when you are dealing with the sum of the density functions, optimization is going to be difficult. And so we have to actually introduce latent variable to make our optimization easier. Okay, let me pause here just to say something. As one student mentioned, there's a lot of optimization going on. And this is what kind of related with one of the comment or question a student posted on Piazza. Should we call this statistical learning or machine learning, or just optimization? And because those problems involve different aspects. And so yes, optimization is everywhere. Okay, so let's first look at how we're going to write down the joint likelihood, a joint density for each one of them. I think so this is equal to xi, x and z. Let me subscript and drop that, and drop that subscript. This is equal to, by factorization, is equal to, you first generate your latent variable and you generate your x given z, right? Here, I just put a subscript theta, just try to tell you all those distributions or probabilities will depend on the parameter. And well, how we generate, what is the probability, like the product of this? And we know actually can be written as this kind of a case by case, because if z is equal to 1, what's here is going to be this component, which is basically P1 and the normal and the mu1 and the sigma, if z is equal to 1. Now, if z is equal to 2, it's just going to be a different product here. Okay. Now, we don't want to have our density function have this like, kind of if commands, because it won't be, it will not be easy for us to do the optimization. So instead, we're going to write our density function in the following way, which we're going to use. Let me just write it here. So, let me introduce a different way of writing this too. So make it easier for us to take log, because I want something as a product. So how we compute, how we write the joint distribution of x and z. And here my z is uppercase or lowercase, it doesn't matter. What's matters is later on when we talk about expectation. So it's okay, you can think of this as lowercase. So this is equal to, I'm going to write something like this. It's going to be P1 and the normal density plug in mu1 sigma, and raised to the power of an indicator z is equal to 1. And then times P2 normal x mu2 sigma, and raised to the power of indicator z is equal to 2. Okay, so this is exactly same as this case-by-case expression, but what's nice about this is everything's a product, because usually when we do optimization, we take log. So let's look at what is the log form. If I take log of this density function, because that will be the log likelihood for one observation, is going to, once I take log, this part, I can drag it down. So it's an indicator of z equal to 1 times a log of P1 and the log of this density function, right? And so it's going to be a log of, let me write down the density function. Log of this one, and I'm going to start just give you the answer. And so log of a multivariate density function with two-dimensional mu1 and sigma is actually equal to minus a half log of the determinant of sigma and minus a half x minus mu1 transpose sigma inverse x minus mu1. Okay, don't worry, the determinant sounds like scary here, and don't worry about this at this moment. So this is how we take log of this. Now, the multivariate normal, when I take, there is a like 1 over square root of 2 pi, but that's going to be a common factor in here and here. So once I take log, that becomes a constant. Usually has nothing to do with optimization. So I drop that 1 over 2 pi factor, okay? Now you can do the same, and if z is equal to 2, you get similar expression here, right? Okay, so that's, this is our, so we haven't get to the EM algorithm step yet. It's just preparation right now. So this is our, make sure that distribution, our parameters, what our data look like, but we want to add the data with latent variables z1 through the n, and eventually we're going to work with the joint likelihood involving both x and z. Now to get us prepared, let's first write down what is the joint for a pair, only single observation. And we have a form like this. And if we take log, because we know we're going to eventually work with a log form, and it look like this, right? Okay, so now we're going to start doing our EM, because the purpose is just try to, find the likelihood, find the parameter which maximize the likelihood. So let me, this is our data and our EM step, very step and 1, which is the log of the joint likelihood. Okay, likelihood. So what a joint likelihood basically is just log of the those observations given the latent variables are independent. This is different from the hidden Markov model because my z's are just Bernoulli random variable with one with equal to 1 with probability p1 and 2 with probability p2. So each of the pair are independent. So their log likelihood basically is their likelihood is going to be a product from 1 to n. And xi, I'm going to keep my z as uppercase. And this, once you take log, it becomes, summation. I from 1 to n, and log each individual of them, right? Now, we have calculated this individual one before, okay? So let me just plug in the expression. So I'm going to use this expression for each xi. So this is going to be equal to sum I from 1 to n and an indicator where zi is equal to 1 and times log p1 minus a half log determinant of sigma minus a half xi minus mu1 transpose sigma inverse xi minus mu1. Okay, that's only this line. I also have to do this summation where indicator, so zi equal to 2. So this is a summation on both of them. And let me do that. And times now is log p2 minus a half log sigma minus a half xi minus mu2 transpose sigma inverse xi minus mu2. Okay, so let me do it. We sum over n observations, indicator of zi equal to 1 or 2, that will determine whether it's a log p1 or log p2. And this factor is the same because all the components, like the two different normals, have the same covariance matrix. Here is xi because we're talking about the ith observation, but it's the first component, so it's minus mu1. And here is the same xi, but we're talking about the second component, so it's minus mu2. Okay, so this is our joint likelihood. This is the very first step of the EM algorithm. And now we cannot directly maximize this because the zi's are not, we cannot observe zi. We only observe the x's. Those are the lowercase. And we try to pick the p1, p2, sigma, mu1, mu2 to maximize the expected version of this. So what we're going to do next step is the E step. In the E step, we want you to take expectation of this, meaning once for indicator variable, once we take expectation, that becomes the probability, right? So at the E step, So let me keep this one here. So I'll bring that slide back. So the step 2 is called the E step. In E step, we wanted to basically find out the distribution. We want to find out the distribution of Z1, which are the latent variables, given the data, because we always do our inference condition on the data, and some initial estimate of the parameter. So the EM algorithm is always an iterative algorithm. Let's assume we initialize our parameters. Now, given the data, given the x's, what are the distribution of the z's? These are only binary, and you can actually further and find out they're independent. So basically, each of the zi, given, you only need to given the observation xi and some initial estimated parameter, it's actually going to follow a Bernoulli distribution with probability P1. Well, let me just do, sorry, it's so weird. Let me rewrite this page. So step 2 is an E step. So we basically wanted to, we have all the latent variables, given the data and given some initial parameters, we want to find out what is its distribution. And turns out in this case, they are all independent, but follow different Bernoulli or multinomial distributions. So each of the zi, given xi, and given some initial value of the parameter, it actually follow a multinomial with probability P1, P2. I didn't say Bernoulli because by Bernoulli, we often assume the outcome is 0 or 1. So multinomial means this, this random variable can only take 2 different values, 1 or 2 with probability P1 or P2. Of course, some of these 2 should be 1. So this is the P1, P2, let me do PI1, PI2, because for different observations, this conditional probability will be different. So this, we just need to find out this PI1 and PI2. And how we find them? Actually, that's easy because this is just a conditional probability. And we already know, this is actually the calculation we've done in our base formula in coding 1. So what is the probability of zi equal to 1 given the data I? And let me put the parameter here, okay? This is a conditional probability, and although this one is continuous, as I mentioned for coding 1, you can still use that, can treat them as a discrete, meaning the conditional probability is just equal to the joint and divided by the marginal. And now how we compute the marginal? The marginal basically is equal to zi equal to 1 xi plus zi equal to 2 xi, and the numerator is zi equal to 1 xi, right? So now how you compute each of this joint? Well, it's just equal to this, for example, this one. How you compute this one? This basically the probability of you observe zi equal to 1 times the density of xi given zi equal to 1. So this term, you're going to find out is just equal to P1. Now, let me put a superscript 0 because those are determined by this initial estimate of the parameter, and times a normal density of xi and mu 0 and sigma 0. So this will be the term here and here, but for this one, it's very similar. You just replace P1 by P2, replace mu1 by mu2, and sigma is the same. So this is how you compute those probabilities, P1, P2. So that's the E step, okay? Now, once you have this P1, PI1, PI2 calculated, so this is equal to PI1, because that's the probability of the ith observation is in group 1. And once you have this one, you know what is the PI2, which is basically 1 minus this, right? So once you have those, you finish your E step. And the next step is a maximum step. What is the maximum step? Remember, at the very first step, we calculated the joint likelihood. And at that time, I said we cannot directly optimize this because there's an uppercase Z involved. We don't know how to compute. So at the E step, once we are done at the E step, at the M step, we basically take expectation of this, average out those uppercase Z. Now Z only appear here. When you take expectation, and basically this, what is the expected value of an indicator? This becomes the probability of Zi equal to 1. This is the probability of Zi equal to 2. So at the M step, you basically have to deal with the same objective function. I basically at M step, you basically deal with objective function, just replace this by your PI1 and this by your PI2, okay? So that's what you've done at the M step. Now, those are numbers you calculated. So the whole thing is basically objective function involving P1, P2, mu1, mu2, and sigma. Okay, so you just try to find P1, P2, mu1, mu2, sigma to maximize this. Definitely is a lot of work, but don't worry, there is a note you can check. And let me tell you the answer, and then I'll show you in that attached note from another professor where you can find out how those numbers are computed. So it turns out for P1, this is a number. So P1, the optimal estimate for P1 is just going to be PI1 is just going to be the average of PI1, meaning you sum over the probability over I, you divide it by N. And you take this sum over the probability over I divided by N. That's your P2 estimate. Because what you in the E step, you have computed that, well, for all the N observations, this is a probability, the ith observations in group 1 or component 1. And this is the observation for the ith data point in group 2. Now, once you compute this, so you can sort of arrange this as a column for observation 1, 2 until N. So this is a PI1. You have another column for PI2. And basically you average those N numbers. That gives you the best estimate for P1, because sort of on average, what is the chance of your in first group? And this is the average of your chance in second group. So this is how you get P1, P2. Now the mu1, mu2 will be a weighted average using this weight. I'll just show you. Now tricky things about sigma. So let me switch back to Piazza. Wait, let me. Where is my? Okay. Okay, so if I look at coding assignment FAQ, this one, okay. So you can, this give you a lot more background on this. So basically, he's talking about, the K, there could be more than 2 components. So the R here is basically the P, I should have used R. So this basically the conditional probability for the nth observation in the Kth component. So you basically average them, you get So that his pi is my p, pi 1, pi 2 will be p1, p2. And how you update the mu, basically weighted average. You just replace, you have your for all the n observations, and how you estimate the, what's your best guess for the first, the mean of the first component. You basically look at, for every observation, look at what is the probability of in, the case group. Let's think about case 1. So what's your probability in group 1, and you do a weighted sum and you normalize by the weights. So that will be your best guess for mu1, and you can say similar to mu2. Now, in his case, the sigma is different for the two groups. But in our case, in coding 4, I assume sigma is the same. So there's no, so basically how you're going to do that is you basically have to sum over k and divided by n. Meaning, let me switch back to my slides. Okay. So when you try to update your mu1 is basically, let me just see one more thing. So mu1, the best guess for mu1 is you, for ith observation, you know your probability in the first component, and you weight xi, and you sum over all I observations and divide it by the weights. This is how you estimate mu1 and mu2. Now, how you estimate sigma. Now, sigma is a matrix. In order to understand how to derive a MLE to maximize, to find maximum likelihood for sigma, you can do a Google search, and I can also add a link in wiki page, like how to find MLE of covariance matrix. Now, the answer is, in this particular case, what you have is for every observation, you have to, so how you get your sigma, what is your best guess for sigma? Sigma is 2 by 2, right? 2-dimensional. So what you're going to have is you first look at every observation, because we know how we compute sample covariance matrix, is yi minus its mean. Now this is a 2 by 1 vector, is a column vector, and you times its transpose. Usually, if we talk about sample covariance matrix, we just do this and divide it by n or n minus 1, depending on you want to do the MLE or the unbiased estimator. But in this case, for every observation, there's a probability you're in the first component. So we have to actually add the weight here, pi1. So when we compute the covariance matrix, we look at your contribution, like basically how far you are from the mean, you get a column vector times its transpose. This gave us a 2 by 2 matrix. Now I weight by your probability from, cluster 1. And in that note I just showed you, then they basically further minimize, like divide it by just sum of the weights. That will give you the estimate for sigma subscript 1 for the first component. But now, since we assume the sigma is the same, so we actually have to sum over I from 1 to n, pi2, because 1 or 2, you have the same covariance matrix, so you have to sum them together. Now it's mu2. When I say hat, means that's plugging the estimate you have. So this sum, now you have to divide it by their weights. But now remember, because each pair of them, sum is 1. So if you sum over all the weights, they should just give you n. So this will be the estimate for your covariance matrix. Now you can do a screenshot on this. Okay. And so once you have your, in your program, you just do your calculate in the E step, you basically have to compute those probabilities. And each one is like likelihood times a normal. And then once you do that one, you have your M step to update those parameters. Then you finish one iteration and you repeat. And once you finish your code, you can sort of benchmark with one-step iteration from the building algorithm and just make sure your calculation is correct. Okay, I think I run way over time. Any more questions for this?
I have a quick question. You distinguish between small z and capital Z?
Right, small z and big Z.
Yeah, big Z. So big Z, so I didn't, what is the distinction? Big Z is all the Z's together and small is
No,
just one?
no, big Z's. So here's what you have to think about this. Remember coding assignment 1, right?
Yes.
Coding assignment 1, where how you generate a data from a mixture with 10 Gaussian distributions.
Yes.
You first generate which component you are from, a number from 1 to 10.
Yes.
And then based on that, number, which component, the indicator, you go to the corresponding normal and generate that go to the corresponding center and generate normal from that distribution.
Yes.
So when you generate your data for coding 1, for every observation, which is a 2-dimensional point, which you showed on your plot, there is a xi and also zi. Zi is the indicator, taking value from 1 to 10 in coding 1. Now, because you generate data, so you know which component each observation are from. This is what the data look like. In that case, the z is a lowercase z because the realization of you observe which component you are from. Now imagine you generate those data and you only give the x to your friend. Now, and you tell your friend, okay, my data are generated from a mixture of 10 Gaussian distributions. And could you guess what are the parameters for that mix and weights and the mean of each Gaussian and also the covariance matrix? So that's the game, that's the coding assignment 4, although I reduced to 2 components. Now you can see, in this case, when you give the data, only pass data X to your friends, your friend wouldn't know, for the first observation, for example, X1, he wouldn't know which components are generated from. So when he's trying to do this calculation using the EM algorithm, he has to keep the Z as an uppercase because in statistics, we often use uppercase to indicate a random variable, and your lowercase means a particular value. In this case, I just want to keep remind you, my Z is actually unknown because I don't know which component the X1 is generated from. This is why later, when we have this likelihood, where is the joint likelihood? In this case, this is a full likelihood, but we cannot really, I think I use a different one. Right. So when we have the likelihood, usually when we do MLE, once we have the likelihood, we should be able to, just try to find the parameters to maximize this. But you cannot because this one is unknown. So you really don't know the expression of this likelihood. What the EM algorithm is trying to do is try to take expectation of those Z's. Now, the reason is there is a chicken and egg problem because in order to know the distribution of Z, you have to know the parameter value, but you don't know the parameter value. So this is an iterative algorithm. You initialize some parameters, assume they are true, and you calculate the expectation, and then update a new set of a value for the parameters. Now treat them as given as your initial value and go through your machine again until they converge.
Thank you.
Okay. Any more questions? Okay, so I'm going to stop here. Now, again, post your questions on Piazza, and we'll find time to provide details through this office hour on weekends. Okay, and bye. And coding 2 is due tomorrow.
Thank you, Professor.
Thank you.
Bye.
Thank you.